So one of the frameworks that we've set up all semester long is that there are two really fundamentally important problems that we're going to deal with in introductory level physics. One of them tends to be using Newton's second law to think about forces and how we change momentum. The other is thinking about energies. And so if you think about what we've done with fluids, again, we've basically set up two big problems. One that's thinking about the buoyant force as a way to think about forces and work our Newton's second law problem. The second is Bernoulli's equation. So Bernoulli's equation, as we'll see as we go through this derivation, is a way to think about energy and how it's conserved as a fluid flows through a pipe. So let me start by taking some chunk of fluid. Let's let that be an ideal fluid, so it's going to be incompressible. It's going to flow through a pipe, but this time what I'm going to let happen is I'm going to let that pipe, its diameter will vary. So notice the pipe is larger down here than it is up here, and I'm also going to let its height vary. So here, simply I have initially the height of the pipe is lower than what it ends up being at the end. Okay? But I want to think about what's going on with this chunk of fluid. So again, I've got some little chunk dV, right? Some little volume of fluid. That dV is going to be given by some area as it flows through my pipe times this little vertical distance that I measure as the pipe flows past at some speed v. And here, again, it's that same chunk, but now because I have a smaller area, that means it's got to be flowing at a faster speed from my continuity equation, which means that now this length of the tube has to be longer. So I have sort of two different cylinders here. They have the same volume, but they've got different areas and different lengths of the cylinder. I know that at this end of the pipe, again, there's going to be some force from the other fluid that's over here to the left that's going to generate a pressure. That pressure is going to be pushing this chunk of fluid this way. And then over here, again, there's fluid out on this end of the pipe, and that's going to generate a force that's pushing to the right on my tube of fluid that's sitting up here in the upper part of the pipe. So what I want to do is I want to think about what's the work required to move my chunk of fluid from this point to this point. And so what I'm going to keep track of are three different things. The first one is the work done on the fluid. And so again, I know that the work, again, I want to think about, I'm moving some differential element here, so I'm going to think of this as a differential work term, and that's going to be this force pushing over here that's moving it in the direction. So this force does positive work because it's pushing in the direction my chunk of fluid is flowing. It's given by what that force is times the displacement of the fluid. This force does negative work because, again, it points opposite the displacement. That's where that minus sign comes from. I've got the magnitude of this force that's pushing back on my upper tube, again, times its displacement. And again, these displacements are different because my little volumes of fluids are flowing at different rates at each point in the pipe because they've got different diameters. Well, the forces, pressure times an area. So force 1 is pressure 1 times area 1. Force 2 is pressure 2 times area 2. And now when I think about this, I see that what I've got is an area times that little length of the tube. So in both cases, this is dV. So what I get is my differential work term is really pressure 1 times that differential volume element minus pressure 2 times that differential volume element. So this is the work done on the fluid. Well, I can also think about how the kinetic energy of the fluid is changing, right? It's clearly moving at a different speed here than it is there. So change means final minus initial. So here's my final as it ends up at this space. Here's my initial down here. So this is final minus initial, which is giving me a differential change in the kinetic energy. And so again, I'm thinking about some tiny little element of mass that I'm moving to get this differential element of kinetic energy. And so this is really just 1/2 mv squared, where instead of that being a discrete piece of mass, it's now the mass of this little chunk. When I calculate that out, these little chunks of mass are the same. They're both given by density of the fluid times its volume. And so I can think of this differential change in the kinetic energy of the fluid as it goes from this point to this point is 1/2 the density of the fluid times the volume of my little fluid element times v2 squared, the final speed squared, minus, same thing, 1/2 times the density of the fluid times the volume of my little element times the initial speed squared. Well, the last thing I can think about is how the gravitational potential energy of my little fluid element is changing. So again, this is going to be a differential change in the gravitational potential energy. This is going to be final minus initial, so it ends up here at some greater height. I'll let this down here be the reference, some reference point. So this is where I'm setting the 0 height to be for gravitational potential energy. And so again, this differential element is just take my little chunk of mass times gravitational acceleration times its height. At the end, it's at height y2, minus initial gravitational potential energy, again, same little element of mass, times g times my height y1. So again, those mass terms I'm turning into density times volumes, and so I get rho dv times gy2 minus rho dv, there should be a g here, times gy1. So I know that the work done is telling me how I change the total energy of my system. So this just says that what the work done on my system does is it changes the total energy, which means it changes the kinetic energy and it changes the gravitational potential energy. So plugging in what we just calculated out, here's my work term, equals my change in kinetic energy plus my change in gravitational potential energy. And all I'm going to do is rearrange this so that all my 1 terms come over on the left, all my 2 terms I leave over on the right. And so what I notice is I've got pressure 1 times my little volume element times 1/2 rho times my volume element times v1 squared plus the density times my volume element times g times h1 equals, it's the same expression over here, it's just now instead of 1s there's 2s. So it's the pressure P2 times my volume element plus 1/2 rho dv speed 2 squared plus rho dv times g times that second height. And again, I notice that every single term in that expression has my little differential volume element, so it divides out and I'm left with this equation. It tells me that the pressure plus 1/2 rho times the speed squared plus the density of the fluid times g times whatever its height is relative to some 0 point is equal to, same thing, it's just now where there were 1s there were 2. So pressure 2 plus 1/2 rho v2 squared plus rho g y2. This is known as Bernoulli's equation. And what you can see is it's basically telling you that the sum of the pressure and the kinetic and gravitational potential energy densities. So again, this isn't 1/2 mv squared, it's 1/2 mass per volume squared. So this is a energy per volume, just like this is an energy per volume. That's an energy density. So that if I add together the pressure plus kinetic energy density plus the gravitational potential energy density, that's the same at the beginning as it was at the end. So that if I have an incompressible frictionless fluid, so an ideal fluid, the sum of the pressure plus the kinetic and gravitational potential energy densities is constant, and that's true both in time and along a streamline. So you can think about this as Bernoulli's equation says that this is true in time and if you pick the right way to keep track of what's going on in space. Effectively, Bernoulli's equation is conservation of energy for a small volume, our tiny little volume of an ideal fluid. So we had our buoyant force as a way to think about adding to our Newton's second law problem, our first big problem for this class. Our Bernoulli's equation, again, is going to be our way to add to thinking about conservation of energy when we have fluid that's flowing.